So you guys do know that the third exam, is coming up very, very soon. And I know you don't want to hear that because we just finished one, but it's literally in 2 weeks from today. So not next Monday, but the Monday after is exam 3. So that tells you that you have no time to chill. Like you've got to keep going. But that also should tell you that it's only 2 weeks from today, which means that the stuff that we have to cover is not as hard. I will say that again, like usually exam 2 is really difficult, one of the most difficult ones in the entire semester. It starts to get easier. In general, people tell me that it starts to get easier. And, like for example, the stuff that we have to cover in chapter 5 is literally based on one equation, the entire chapter. So it's very different than chapter 4, where there was like so many different concepts we had to learn. So hopefully, if you guys are going to stick around, hopefully you'll find it that it's not as stressful as chapters 3 and 4 were, and you'll do hopefully better. I did not start. Well, that's not true. I did start grading them today, but I just started today. I will have them hopefully done by today, by the end of today. So you'll see your grade by the end of today. That is my goal. Midterm grades are due tomorrow. So that's why I'm trying to get it done before tomorrow. And what I've seen so far, I've seen improvement, which I like. I've seen improvement in how a lot of people, and again, I haven't finished, but what I have seen is I've seen improvement in how you explain or give me your answers, which is good, right? Doesn't mean that you got them right, but I see improvement, which is good. That is a good trend. There's still a lot of people that leave a lot of things blank. It's not going to help you, but so far I'm not super ecstatic about the grades, but there are some like shining moments where I'm like, oh my gosh, yeah, okay, fine, you got this wrong, but you got this, and that right, which is really good. So that's my synopsis on the little that I have seen thus far. I'm not, like I said, I'm not going to go over the test, but if you guys, I gave the first section, like, I don't know, 5 minutes or something, just to, if you want to vent, if you want to say anything about the test. Did you think it was super uber hard? Did you think it was easier? I gave you multiple choice, which I haven't done since the first year I got to Tuskegee. So, and I did that so that you hopefully would have time to finish and not, I made, those are easier. I mean, I really do believe that the whatchamacall, the multiple choice ones were easier, and the bonus I thought was easy. So I hope that would help you. Like I said, when you saw that 55-point question and you were like, holy crap. So does anybody have any comments on the exam or no? And feel free to say whatever you want.
I got a comment.
Okay.
So I already told you that I cried in my video, right?
Yes, and I haven't seen it yet. Yeah.
So off of that, it was actually a whole lot easier than the first exam. It was just the titration questions threw me all the way off. And I think on number one, I didn't even notice it was 55 points until after, and I was like, why would you do this to me? And then I probably have some miscalculations. Like I got the concept, but I probably have like a little bit of like small mistakes in there, which will probably mess me up. But at least I got the concept. And then I did the bonuses, but it wasn't. It was. You said it would be astronomically hard, and it was creepily astronomically easier than the first exam.
So that makes me happy because that means that you are learning your concepts. You are learning your concepts. That's stupid mistakes here and there are not going to make you an F. For example, I don't know whose paper it was because I grade all. What I do is I grade all number ones together, so I can get so I grade them fairly throughout the class. Anyway, I don't know whose it was, but this person got a wrong molecular weight for something that they were doing stoichiometry. They got the wrong multiple ratio, but they have it correct on their reaction. So and they have it correct in other parts. It's just that she, oops, it was a girl, but she just put it wrong, and she calculated the molecular weight wrong. But that stuff is not important. I mean, yes, it's important, but it's not like, okay, 1 point off here, 1 point off there. But the bulk of the freaking thing, she understood. So that's great. That is great. So then why did you cry, Evan? If you thought it was easy.
Okay. No, okay. Cause I was my aunt was she took chemistry in college and she taught it. So I was on Zoom calls with her after every single one of your classes at nighttime studying and trying to make sure that I understood it better.
That's awesome.
And we never got to get to titration, so I had to look at it and review it myself. I didn't understand it, and I couldn't call her because she had to take my grandma to the doctor.
Mm-hmm.
So I took the test, and I started feeling bad because if I failed the test, I would feel bad because I put in so much studying time and questions that I asked her, and I didn't pass the test.
Oh no, don't. I wouldn't stress you're putting way too much pressure on yourself. The fact that you're doing all of that extra work after every class is magnificent. So I think that I don't know, because I haven't seen everyone's exam yet, but don't stress out and don't beat yourself up. If you're working so hard, you'll see an improvement. You will, I promise you. And if you don't, then it's just, we can talk about it and we can see where something that you're maybe, need to do, and that's it. But I think you'll be fine. Anybody else want to talk about or have any other comment?
Something I want to say.
Okay.
I just feel like, I don't know. You said this is supposed to be the hardest one, but I just feel like exam 1 was out to kill. And I don't feel like this one, I feel like this one might have been like a little harassment, but nothing too crazy. And
I harassed you, just a little bit of harassment.
and I don't know if you saw it, but I feel like a whole new student, but compared to like my like workout papers, my first ones that I sent compared to the ones I just sent, I feel like I can finally
like you were here and now you're over here.
Yeah, like I feel like I'm finally off the bench. Like I can actually compete now. But yeah, I feel like it was easy to understand. Like you could look at one question and be like, what? But now you can be like, oh, I'm getting bits and pieces of it.
That's
so
good.
I feel better about this exam.
That's good. That's good. And it's funny that you say that, because I had a student year ago. Well, she was in my class years ago, but she works for me, so I love her, right? But she was the only person that said from the get-go, like, no, exam 2 was easy. She thought and I understand why exam 1 was hard for you, Jayla, because it's the first tournée exam. You don't even know what the hell to expect. Even if you have old exams, you're really not really prepared for it until you go through it. But anyway, she said that exam 3, which I don't want to tell you so that you freak out, but she was like, I hated exam 3. I didn't understand an exam 3. It was so much harder, but she got like an A in exam 2, which is completely abnormal to everybody else. Like usually people do really poorly on exam 2 because there's so many concepts. But the fact that you think it's easier, maybe you didn't get, perfect, but you're doing like exactly what Evan, like you guys are working, you guys are doing, like you said, you're able to get off the bench now and at least play a little. So that is improvement. That is what you guys need to be seeing, and say, yes, fine, maybe it's still hard, maybe it's not like uber easy, but it's not undoable. So whatever it is that you're doing, if you guys improve, and it might not be the grade that you want, but you guys are improving, then whatever it is that you're doing is working. Maybe you just have to do more of it. But if you get a worse grade, then you guys we need to talk. We need to talk, because the drop date is October. I don't know when
October 20th is October.
Thank you. It's October 20th. So you have to decide. I don't know that I'm going to have the exam 3 ready and graded for everybody by one day after. So you guys really do have to decide after this grade comes up whether you guys want to stay or not. I would hope that before you leave, talk to me, because maybe, you know, you guys are probably pretty hard on yourselves. So, and it's not, you know, I can sit down and I can look at your personal grades and just kind of give you my opinion. But, you know, if you feel like you're improving, then you're probably improving and you're probably doing a good thing. You're probably doing something good. So just keep doing what you're doing. I really am glad to hear that. I hope that the grades reflect it. I really do hope that the grades reflect it. And, but what I've seen so far, just the explanation of things or just the writing of things seem more coherent. I got a bunch of jibber jabber like in the first exam. I was like, what in the world is this? Like, I don't even know if this is chemistry. I don't know what they're doing. So it does seem better thus far. But of course, now that I said it, I'm jinxing it. And now everything else that I see is going to be bad. But I'm glad to hear that, Jayla. Anything else? If not, we probably do have to get moving. But anybody else want to say something quick or no? No, you guys are good. Okay. Well, we are starting chapter 5, and let me share. I thank you for sharing your thoughts and your opinions and your whatever. For those of you that did, where is, oh, Lord have mercy. Of course, I don't have it open. My God. Sorry. Tuskegee, CHEM231, lectures. Okay, here we are. Sorry, here we go. Okay, now where are you guys? You're over here. Share. Take that off. Okay, so, oops, let's make that a little bit bigger. Oh my God, what the? Sorry, guys. Okay, and let's make that into not this. Let's make it into this. There we go. Okay, you guys you can see it, right? Yeah.
I can't.
Okay, good. All right. So, chapter 5. Let me preface by saying it's super easy. It's all based, this entire freaking chapter is based on one equation, which we're going to start talking about now. But a little introduction of gases is usually helpful. We're basically going to be manipulating and learning about ideal gases, right? So there's non-ideal gases. I think you have a little section in the back of chapter 5. You don't have to worry about that.
Dr. Tornay?
Yes.
Okay, you can hear me?
Yes.
I cannot see the screen.
Okay, so I think, because everyone else can, so I suggest that maybe go out and come back in. Maybe it's just like it's stuck or something.
Yeah, because I thought when you were sharing your screen, like a notification popped up on your screen that Zoom stopped working, but mine had like put this whole little letter thingy that Zoom stopped working. So I don't know. So I'm gonna come back.
Okay, yeah, come, because everyone, hold on, before you leave, everyone else can see it, yes?
Yes.
Yes.
Yeah, okay.
Yes.
So yeah,
Okay.
so it's something with your computer.
All right.
I'll see you later. I'll see you back. Okay. So anyway, it's just a manipulation of ideal gases. And as we're going to hopefully get to today, you'll see that this ideal gas equation, PIV-NERT, that's what I call it, PV equals nRT. But anyway, PIV-NERT is a combination of 3 different laws that 3 different scientists were working on 3 different things independently, but they all related to the same thing, which is really, really pretty cool. What else can I say about gases? So I think the beginning of the chapter talks about, gases right now or atmospheric gases, for example, are very important because what's in our air right now is very polluted. We have ozone layer issues and stuff like that, and a lot of pollution. So there's a lot of atmospheric chemists that are very concerned about what's going on right now. But it is basically, yeah, I think that's all I got to say for introduction. Any questions? No? All right, let's get started. So this is in your book. This is periodic table, obviously. The things that are in blue are the elements that exist as gases at room temperature and 1 atm. So normal conditions, yeah? 1 atm, 25 degrees Celsius. Most of these guys you know already. A lot of them are, part of the Broncliffe. But what you see on the monoatomics are obviously the noble gases. But everybody else in gray is not a gas at normal conditions, meaning 25 degrees Celsius and 1 atm. And that goes to show, I mean, that should make sense because ionic compounds are usually solids. A lot of them are, usually solids. And if, for example, sodium chloride, I've talked about a lot, is a solid at room temperature. And if you wanted to melt salt, like you would have to raise it to like 800 degrees, right? Melt it, not even vaporize it, because we're talking about gases. So to vaporize it, you would have to even put even more heat. So typically, strong metal ionic compounds are not gases at room temperature. So you have to provide a lot of kinetic energy for that to happen. But that's it. Any questions on this? No. Okay, great. So part of the introduction is just kind of give you some physical characteristics of gases. These are pretty logical. They're pretty common sense. But gases assume the volume and shape of their containers. That is very true. The story I gave in the first section is a true story. When I was a kid and I used to live in Puerto Rico, my mom used to take me to the mall, and the mall's pretty big. Like, it's not super huge, but it was pretty big. It had like different wings or whatever. And she would always park on one side, which was the Sears side, which I don't think even Sears exists anymore. But anyway, was the Sears side. And we would go in, and there was this popcorn guy that would serve, be there all day serving popcorn on the other side of the freaking mall. But every time we walked in the door on this side, like, I would smell it immediately, which is, if you think about it, that's exactly what this thing says. Gases assume the volume and shape of their container. Those gas particles or the vapor particles that were happening from the freaking popcorn were traveling and encompassing the entire area that it was allowed to encompass. So be it big, be it small, they still take up all the volume that they're allowed to take, which is pretty cool. And my nose was pretty big, so I have good nose things. I have a good nose to smell things. But anyway, so that's that. Gases are most compressible state of matter, absolutely. So they're very, very tiny, and you can compress them down into a very small area, which is kind of like how pistons work in your car. But that is one. Another one is gases will mix evenly and completely when confined to the same container, which is very different than liquids, and obviously very different than solids. Oil and water is a big, super good example, right? Like, they don't mix. So gases don't do that. Gases, it doesn't matter who you are, and they're indiscriminate, right? They don't discriminate amongst anybody. They just mix and live happily ever after in the same container. There is some that say, or not some that say, if you compress them down enough, right, there's going to be some interaction between them because you're bringing them closer and closer together. But that's not what you guys are concerned about right now. You're concerned about normal conditions. So normal conditions, they're going to mix evenly and completely. Doesn't matter who's in that flask. And then the last one is gases have much lower densities than liquids and solids because, again, they're so small and they occupy such big volumes compared to their size. Their densities are really, really small, okay? Which is different than liquids and solids, obviously. Any questions on this?
I have a question.
Yeah.
So it's about the first characteristic. When you said the gases assume the volume and shape of their containers, like you said when you were at the mall and it assumed that huge volume, did that change the amount of like molecules, I guess you would say, that there were in the air? They just expanded?
Yeah, no, not if they just traveled, right? So it doesn't change the number of moles, because that's what it is. It's the number of moles that whatever machine was making. It doesn't change it unless he makes more popcorn. But no, the fact that the volume is big has nothing to do with the changing in molecules. No, it just if you put a gas in a flask that's on the screen, it's going to fill the whole thing. But then if you get a bigger flask, it's going to fill the whole thing, just be more spread out, maybe look a little bit lighter. Does that make sense?
Yes, thank you.
Yeah. Any other questions? Okay, so this slide is literally, oh no, this slide is literally so you guys can, for the first time and officially, see the units of pressure. Okay, so we're going to be talking a lot about atmospheric pressure and yeah, just pressure in general, right? So it is one of the variables of the Pivner equation. So for those of you that are not very used to pressure units, that's what the slide is for. Do you have to memorize these? No, because they're on your sheet, right? You just have to learn how to use them and how to convert from one to the other. So depending on what I ask you, you can use your conversion sheet to convert between torr, millimeters of mercury, Pascal, whatever. Okay, so does anybody know, well, just to kind of be a little bit more complete, the Newton is the unit of force, so that's this guy. If you guys in physics, you should know that variable, but that's there. And Pascal is the SI unit of force, right? So no, my bad, of pressure. Yes, Pascal is the unit of pressure, my bad. And Newton is the unit of force. So when you combine those two together, that's what can give you the rest of the conversions that you have here. Do you have any idea what this is there? Does anybody have any idea? Because it's in the book, but did you guys actually read it? And do you know what it is? Come on, anybody? Nobody? The story doesn't mean anything if you guys haven't read. Okay. Well, that is a barometer. It's like the world's first, oh, somebody, you can, instead of, thank you, Kennedy, but why are you afraid? Just talk. So can you say anything about how that barometer works, Kennedy? No, you can't talk. Unmute yourself, girl. Oh, your mic is broken. Gotcha. Okay. So it is a barometer. A barometer measures atmospheric pressure. You guys might not notice, but we live under a mountain of gases, right? So you don't notice it because humans are adapted to it, obviously through all the millennia that we've been here, but you guys have tons and tons of gases on top of you. And those gases that are living on top of us are putting a pressure on us. So that is what atmospheric pressure is, okay? And if you think about it, it depends where you live in the world. So for example, I used to live in Miami, which is at sea level, right? So at sea level is at the baseline, pretty much, right? Like at the bottom. And then if I lived in Colorado, which I haven't lived there, but if you lived in Colorado, you'd live up on the mountains. So you have, technically you have less amount of air on top of you if you're up there than if you are at the bottom. So atmospheric pressure is different depending on where you are on the world, depending on what height, what elevation you are. So this little thing that you see on the right here was the first type of device that they used to figure out what atmospheric pressure was, wherever the scientist was at, right? So it's a very simple experiment. What they did is they filled up it's a little tube. Let me move you guys because you're at the bottom of my screen. But anyway, they filled up the little tube with mercury, right? They filled it up all the way, but then they inverted it into a dish of mercury, right? So the thing that's holding the tube, that's a dish and it has mercury in it. But then before that, they filled the tube and they inverted it and put and just let it stand there. When you did that, some of the mercury that was in the tube went into the dish, right? Which created, when that happened, it created like a little vacuum up here, right? But the rest of it stayed. Like obviously you see there's a column there of mercury in the tube. Why did it stay? Because the pressure that the atmosphere was pushing onto the dish did not let what's in the tube go out. So that is how you actually measure atmospheric pressure. And this column here, they measured it was 76 centimeters. When you convert it, it's 760 millimeters. So that is a pressure unit that's a unit of pressure. Millimeters of mercury is this is how much space or how much length, height, the atmosphere is actually pushing on a cylinder or on a tube of mercury. That, and it's different. If you can think about it, that would be different if I was in Colorado, or if I was in Miami, or if I was somewhere else in the Himalayas. You know, it would be different. So that is where they get this guy from, the 760 millimeters of mercury, which is another reason mercury is really, it was useful. I mean, we don't use mercury a lot anymore for like for thermometers. We used to use mercury for thermometers. It was a silver solid, right? Silver liquid. And that's what we use for thermometers, but we don't use it anymore because it's very toxic to us. And now they do thermometers with something else, but that they used this mercury to figure out what the atmospheric pressure was. Can anybody guess why they would use mercury and not something else?
Does it have anything to do with Mercury's like state in certain temperatures?
It does. It does. And it has to do with its density. Like the fact that it doesn't, it's not very volatile, which goes back to what your comment was. It's not very volatile. It takes a lot to actually move it up or down, that's sort of why they used it for the thermometer, but also for this reason too. So, but yeah, it is also because it is stable in a large range, right? And it doesn't explode or whatever. It doesn't vaporize. They need it to be stable from low temperatures to high temperatures. So it has a lot to do with its stability in temperature ranges, but also its density was not. It was one of the highest for the gases. So it tends to be more stable, in certain conditions. So that's why. But anyway, that is a barometer. I'm not going to really ask you stuff about barometers. I just think it's a really cool idea how a scientist did this little experiment, and all of a sudden, that's how we do all of our barometers from that day forward. But anyway, so these are the units, and this slide is just again to show you that as you go up, right? So, as you go up, as you go higher and higher and higher, you have less and less pressure on you. You start at 1 atm, which is basically at sea level, Miami. Up here would be 10 miles up is pretty much where planes are, where planes go, right? So, which actually I don't know that, but it's pretty high up there. But which, if you think about it, that is why they pressurize a cabin when you go on an airplane. You're not able to breathe in such low temperatures, in such low pressures. You can't. You don't have, like, your lungs are not strong enough to bring in enough oxygen that will make your system not go into shock. So I said the story earlier, but in my first section, when I was in college, in grad school, we went to Colorado, and I didn't, yes, I knew about Pivner, but I didn't think about it. Like, I went on a plane, I went to Colorado for a conference, and I used to run a lot. I did. I don't run a lot anymore, but I used to run a lot, like long distance. So I was there in Colorado for like 2 weeks. So I went and I started working out, did my thing, started running. Like, in the middle of the run, I fainted. Like, I literally dropped. And I didn't, obviously I'm fine, I was okay. But when I was in the hospital and they woke me up, like, oh no, it's because, do you usually run here? Like, how long were you running? I'm like, I usually run for like 3 miles. Like, what are you talking about? It's nothing. Oh no, yeah, if you've never lived here, you're not adapted to it, your lungs can't do it, and you went off on a freaking long distance run, which that's not even really long distance, then yeah, your body's going to go into shock. So that's why you fainted. I was like, oh, okay, great. So, and you see that sometimes too with people that soccer teams that for example, that go into like Ecuador and they go into the mountains. The people that don't, like, go to play them, you can see that the players that are not from the mountains are like dying. They're dying of, like, they're so tired because they have to work so much harder to do what the other guys are doing because they're adapted to it. But anyway, that is why they pressurize a cabin when you do that, so that human beings can actually survive for a 3-hour flight in that low pressure. So, any questions?
I have a question.
Yeah.
So does it affect you like from somebody coming from Colorado to Florida? Like, does it affect them the same way or?
It makes it easier.
Oh wow.
But you get adapted to it very quickly, right? So it's not like oh, like they wouldn't accept you in the Olympics because you have an edge. No, like if you once you're there for like a couple of days, or like and you practice in it, you'll be I think it kind of stabilizes, it equilibrates, right? So it's not like those people are just higher always than us, they're just better at everything. No, but like for example, if I lived in Colorado, I would just have to get adapted to it, and it would take time. But yes, I do think, and that is me saying, I'm not for sure, but I do think that if they would get on a plane, come to Miami, play a game straight up, they probably have a little bit more energy, wouldn't be as tired, and they would probably even feel it, right? Like I would run 6 miles in the same time that I would run 5 miles or something like that. Um, that's my opinion. That's my theory. I'm not really sure. So, but that's what I think. Any other questions?
I have a question.
Yeah.
So, like, theoretically speaking, if that was true, could we adapt to like the atmosphere in like where planes fly if we were to live there for like if we were to slowly work our way up?
I don't know. That is a great question. Um, I think that the difference is so grand, so grand, because then you could theoretically say, are we able to adapt to, the moon? Do we need, but how many millennia do we need to actually go through Darwin's theory and adapt, right? So in theory, I guess you could, but if you're talking about normal years of a human being, you probably won't be able to in your normal years of a human being. But in theory, because since I'm telling you that it does happen from small distances, in theory we do adapt. Yes, then in theory, I guess we could adapt if we had enough time. But I don't think it's doable with our time span of a human's life. So yeah, that sucks. Unless you can live forever, figure out that, then we can start that experiment. Any other questions? Those are good questions. Okay, so this, I'm not even gonna, well, I'll do it because if I ask you guys are gonna wanna do it, but this question is, do you know how to convert units? I mean, the first paragraph is just the story about the jets, the planes, how they have to, pressurize the cabin, like I just said. And then the question literally asks you, what is the pressure in ATMs in the cabin if the barometer reads 688 millimeters of mercury? So literally you would just, it's a conversion, right? So 68 millimeters of mercury, you would use millimeters of mercury and you would go to 1 ATM. Does anybody remember it? Do you remember what the number was?
760 mercury.
760 millimeters of mercury is how many ATMs?
Sorry, millimeters of mercury.
Is how many ATMs?
1 ATM.
Yeah, I had written it. So that's it. That's literally the question. Then you'd give your answering ATM. It's a dumb slide. I had done this like 7 years ago whenever I got here. So it's just, do you know how to use the units? And that's it. And yes, you will, because you have your equation sheet. Okay.
We still maintain sig figs, right?
Yeah. Actually, now that we're in chapter 5, when we deal with temperature, remember that there's 3 things you don't worry about: sig figs, money, percent, and the other one was temperature. So when we start, now we're doing chapter 5, which we're going to have some questions there. We'll ask you some temperature questions. Don't worry about sig figs, but don't do something ridiculous. Like I would never, I don't know, like I wouldn't give me 17 sig figs. That's ridiculous. Or, if it's clearly like everything else in the problem has 3, give me 3, but I am not going to, take points off for sig figs in a temperature question. All right. So generally the answer to that is yes, unless it's asking about temperature. Okay. So like I said, this entire chapter deals with one equation. At the end of the chapter, we talk about partial pressure, but for the majority, it's about PIV-NERT, right? So PIV-NERT is PV equals nRT. These variables all mean something, right? So does anybody know what the P stands for? What's the P for?
Pressure.
Yeah, right. Good guess, right? We're in a freaking, we just talked about pressure for 30 minutes. What about V?
Volume,
Cool. What about T?
time,
No.
temperature.
Temperature. Yeah, temperature. So time. I wouldn't have guessed that, but time is also, but temperature is what it is, not time. This guy, does anybody know who that guy is? The R?
The gas constant.
Good job, Nia. And N is moles. So moles comes back to haunt us. Always, 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 right? So these three laws that we're, because there's three of them, there's three laws we're going to talk about. You need to know what the laws are. You need to know who the dude, what scientist came up with it. So it's Boyle's law. So, and yeah, that's it. You need to know what they are and what they involve, what the law involves. So for example, Boyle independently was working with pressure and volume back in the day, right? So it's a very common sense law. It really is. But what the law states is that if you hold everybody else constant in this equation, and you have to also realize when I say these sentences, these laws were built, they came up with these laws independently. Okay, so there was no Pivner equation when they made these experiments. Okay, so but what for us, thankfully, I can say, oh, when you hold PV, when you're doing an experiment with pressure and volume, and you hold everybody else constant, then this works. But they didn't know that back then. He was doing experiments with pressure and volume. That's all he was doing. He was working, and he noticed what you see on the graph. I mean, it's very common sense. As you increase the pressure of something, right? Like you tighten it up, you increase the pressure. What happens to the volume of whatever's in there? It gets smaller. I mean, that's a piston. That makes sense. And the opposite is true, right? As you increase the volume, the pressure goes down because they have more space. They're not as cramped. They have more space to move around. The pressure is lower. So nowadays, Boyle's law is basically that. Pressure, it deals with pressure and volume, and it happens, the law actually makes sense when everything else in that equation, nRT, is held constant. So moles, the number of moles can't change. Gas, the R is a gas constant, so that never changes, but the number of moles can't change, and the temperature can't change. So if you have those two things constant, then the pressure and volume will behave like this, okay? I do want to point out that at the end, did I say that already? Yeah, at the end of the chapter, there's non-ideal gases. We don't deal with that. So there are certain instances where that can happen, but you're not worried about that. All you're worried about is normal conditions, normal temperatures, normal whatever. This is what's going to happen. So can anybody tell me if pressure and volume, do you think they're proportional to each other or inversely proportional to each other?
Inversely proportional.
Okay. Is there a way that you can prove that to me using the equation, Pivner? Maybe I didn't ask it correctly, but I would like you to mathematically, or someone to mathematically show me why it's inversely proportional using that equation, Pivner. Would anybody know how to do that? Okay, so what if I made everything else constant, because that's what the law says. If you hold everybody else constant, this will happen to this. So then I hold everybody else constant, so let's just say that this is what I have. PV is equal to 0. I still have an equation, but PV is equal to 0. Would anybody be able to show me or prove to me that pressure and volume are inversely proportional with the
Can I
equation?
try?
Yeah, yes, I want anybody to try, yes.
Okay, since PV are like really like they're being multiplied, right?
Mm-hmm.
So if they're inversely what was the word? Inversely proportional,
Hmm.
then they would have to be being like divided, like one on top of the other. I don't know which one goes on top, which one. I wait, no. Pressure would go on top and volume would go on the bottom.
So you're saying something like this?
Um, I don't know.
But you were on the right track. And so this wouldn't be it. This is no, that doesn't mean it's inversely proportional. For you to prove that something is inversely proportional to something, what you're asking is if I hold this person constant and I do something else to somebody else, to the other person, what happens to the other person that's being held? That's not being held constant, right? So for you to do that in an equation, what I'm trying to get you guys to do, is you were so close, Camille, is you have to isolate the variable, right? So if you do, because I want to know how pressure reacts when I do whatever to volume, I have to separate those variables. So to prove to everybody that they're inversely proportional, I bring whoever to the other side. I separate them. So now they're on opposite sides of an equation. So now that tells you, look right there, if I just bring the V over to the other side, that shows you that whenever I increase pressure, whenever pressure goes up, what's going to happen to the volume? It's going to go down because it's on the bottom of a fraction. So you were getting there, but when you put them on the same side of the equation, like P over V, that doesn't mean it's inversely proportional. This means that it's inversely proportional. So does that make sense to everybody?
Yes.
Yeah, so whenever you see something on the same side of the equation, they're going to be inversely proportional. Those variables are going to be inversely proportional because, again, you have to isolate them. You have to get them on opposite sides of an equation. And that makes sense because of look what's happening when he actually did the experiment, right? Pressure goes down, volume goes up. Opposite is also true. Okay, so that is Boyle's law, super easy. And I'm just going to write this down, BPV, and I'll explain to you why I'm writing that down later when I'm done with the three laws. But Boyle, B, deals with pressure and volume. Okay, so that's why I wrote that. Okay, any questions? If not, let's go to Charles. Okay, so Charles is, and I don't know why this is here. This has been here since I made the slide. I don't know how to take it out, so whatever. Charles was doing yet another set of experiments independently from Boyle. Didn't know Boyle, but Charles was on the other side of the world doing something else, and he was working with temperature and volume. Okay, so he noticed that well, here we go. Here's PV equals nRT. So can you guys tell me, he was dealing with temperature and volume. Is temperature and volume going to be proportional or inversely proportional?
Inversely proportional. Am I
Well, it's
wrong?
proportional.
Yeah, you're wrong. Sorry. They're proportional, right? Because look, they're already on opposite sides of the equation, right? So if I increase, and remember, these laws only work if everything else is held constant. So pretend like everything else isn't there. So all you have is V is equal to T. So everything is already on the opposite side. So if I do something to volume, and since they're equal to each other, since I do something to volume, the same thing's going to happen to the temperature and vice versa. Does that make sense?
Yes. Okay.
Yeah. Okay. So, and this is what he did. He did an experiment. He lowered the temperature and he saw that the volume increased. I'm sorry, my bad. That the volume decreased, which that's exactly what happens if you try it at home. You get a balloon. Don't buy balloons though. Balloons are bad for the earth. I'm serious. But if you happen to have a balloon, you can blow it up outside, tie it, right? And it's blown up, whatever. Put it in your freezer. What happens? Does anybody know what happens? Has anybody ever done that?
It gets smaller.
Like it gets like a freaking raisin, like a prune. It gets all shriveled up. So, I mean, it didn't go anywhere. Like you put air into that balloon, right? And you tied it up. And then you put it in the freezer and then it shriveled up like a balloon, right? So you're not changing the moles. You're not changing the pressure. The pressure is the same inside your refrigerator than outside. So all you're doing is changing the volume, and the volume is changing because the temperature is changing. So, and then you would take that shriveled balloon out of your freezer and leave it on the counter. Guess what happens? In like 30 minutes, that thing is back to original size. It's that's Charles' law at play in your face. So that's all he did. He did not that. He didn't have balloons back then, but he did an experiment that showed the relationship between volume and temperature. So it's very easy. You don't even need to really know it. All you really need to do is look at the ideal gas equation and know that, oh yeah, no, they're directly proportional. They're proportional because they're on opposite sides of the equation. So now we had BPV, right? This is Charles. So this is going to be CTV. This will become clear and after we do Avogadro, but CTV. So Charles deals with temperature and volume. Any questions on this one? Oh, I gotta hurry up. It's 4:25. No questions? No? Okay. So the last law is Avogadro. Amadeo Avogadro became famous because of the stuff that he did here with gases. He didn't become famous because he figured out that it is a mole and how we've been using it with stoichiometry. No. That number was obtained by doing gas experiments. Excuse me. But so he's very, very important in Pivnert. And that is the N. That's the variable N. So this guy right here, that's moles. That's the symbol for moles here, which I know is different. We write moles from up to now, but for here, for Pivnert, the symbol is N, right, for moles. So what have the other laws always dealt with? Here, let me show you. What did I do here? What is common in both of the laws?
Volume.
Right. So what do you think Avogadro's law deals with?
Volume.
And?
Moles.
Right. And are they proportional or inversely proportional?
Proportional.
Correct. So now, and I'll tell you what Avogadro's law is right now, but now let me finish my little thing. So this is, as a student, I had to remember this too, right? Like I had to remember who the scientist was and what the stupid variables they dealt with, right? I didn't know these people. I didn't know these people. So I made up something. So if you go in order, Avogadro, Boyle, Charles, A, B, C, right? And all we're doing is we have these variables to deal with, okay? So go in order. You know that everybody deals with who? With volume, right? Someone told me, just Camille, I think just told me everyone deals with volume. So you would just put V all around. And then what is left? The P, the N, and the T. You don't do R because R is a constant. So the P, the N, and the T, put them in alphabetical order and you have the P, what they deal with. So ANV, BPV, CTV. That also is in alphabetical order. So alphabetical order, and then everybody deals with V. So I don't know if that helps you or not, but that's how I remembered the laws and what they dealt with when I was a student. So anyway, Avogadro's law basically tells you that if everything else is held constant, right? So if pressure is held constant, if the temperature is held constant, R is a constant, so that's always constant. But if pressure and temperature are held constant, then whenever you increase the number of moles, the volume is going to increase, and vice versa. Another thing that the law tells you, which is phenomenal, is, and I know you guys are not going to be as excited as I am when I say it, but Avogadro's law tells you that regardless of the identity of the gas, if you have the same volume of both of those gases, then you have the same number of moles of both of those gases. And I know that it doesn't seem like a big deal, but that's a big freaking deal. Think about what that's saying. It doesn't matter if I have hydrogen, smallest atom in the periodic table, or if I have freaking francium, right? A really heavy metal. It doesn't matter. If I have the same volume of it, I'm going to have the same number of moles of it. Why? It's because of this. It's because of this equation, because of this proportionality, this law that he found, that he experimented on. So why is that important? Is because not because I super care about it, but because you'll see at the end of the chapter when you start doing problems, you're going to see they're going to give you questions. Some questions will give you no information. All they're going to tell you is, I have this much volume and I have this much volume of these two gases, and I reacted it, I gave you a bunch of fluff information, blah, blah, blah. Can you tell me how many moles of the other one I have? And you have no information. All you have is a reaction and volumes of the two reactants. So with that, you have to figure out, use Avogadro's law to actually get you to the answer. So nothing else is going to help you. Stoichiometry can't help you, or whatever it is, because they don't give you any information. All they give you is, my feedback. Anyway, all they give you is the volumes and the moles of one of them. So it's really, it's actually really, really amazing that this dude came up with this stuff. That is it. It's 4:30, so I do have to go. I'm not done, but those are the three laws. So at the end of all of this, right, these people working independently, separate sides of the world, they actually found each other, and they came together at a conference, I believe, but they basically put all of these things together and they made Pivner. That's how the ideal gas equation came into effect. That's how it was created. So we'll keep talking about that on Wednesday. So let me stop sharing, but very quickly, we're finishing chapter 5 on Friday. Okay, so like we're going through this really quickly, and then we're finishing chapter 6 next week. So it's like go, 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 go. But you'll see, hopefully you'll see that chapter 5 is not hard. It's all based around this. So on Wednesday, we're going to just do more problems on Pivner, and then on Thursday, I'm going to introduce partial pressure, which you guys are going to hate, I know. And then we'll do problems on Friday about partial pressure. And then that's it, I think. Any questions? No? Okay. All right, guys. Well, hopefully I'll have all of your stuff graded by tonight. All right. If there's no other questions, then I will see you Wednesday.
Thank you.
Everyone just leaves. They don't even say bye or hi. Thank you. Welcome. Thank you, Camille. There's some people that don't even talk the whole freaking class. I don't know. It's just whatever.
Wait, Dr. Tornay, I have a question.
Bye, Kennedy. I know you're there, darling. See ya.
Have a nice day, Dr. Tornay.
Bye. Thank you, guys. Thank you. Yes, Camille, what's up? Or wait, was that?
It was Camille.
Oh.
I just wanted to know, like, your conference, how did it go?
Great. Like, you mean in grad school, the one that I went to?
Oh, no, the one that I thought you went to a conference. That's what you.
No. Like this weekend?
Yeah.
No, I didn't go to a conference. Did I tell you that? Oh, I lied then.
Okay.
Sorry. Did I say that? Did I say that?
Maybe not. Maybe I confused some things. I thought.
If I did say that, I lied to you. And I'm a big fat liar. Maybe I felt bad because I was going to, it was a reunion. It wasn't a conference. It was a reunion that I went, but it was like personal. It wasn't like for work or anything.
Oh, okay. Maybe it's just because I love conferences. That's why I thought.
I do too. I love conferences. I used to love going to conferences with as a grad student. But yeah, no. I went to a reunion. It was like a friends reunion. We used to all live together in Michigan. So we went back. Everyone went back and spent the weekend. It was really nice.
Okay, cool.
But I haven't done anything. That's why I haven't graded your stuff. So I'm super behind. So I'm going to do it today. All right, darling. Thank you for asking.
You're welcome. Bye.
All right. See ya. Bye.